Okay, so we're also going to talk about the difference between a pinch and a fold. When I ask you to pinch something, you're just going to match it up and you're going to pinch and make a marking where that happens in the triangle, and you're not going to necessarily fold. When I ask you to fold, I want you to match it up and give it a good crease. Here's what I'm talking about. When I want you to pinch, you're going to match up your vertices, and right here you can see I'm pinching, not folding. If I want to fold, then I'm going to have you match up your vertices and create a crease. So just so you know the difference between pinching and folding. Okay? When we talk about an opposite angle and an opposite side, that is going to be the side or angle that is across the triangle from the other. So we have angles opposite sides and sides opposite angles. Would you please all put your finger on one of your vertices of your gold triangle? And would you please trace it across the triangle to the opposite side? So sides are opposite angles, angles are opposite sides. Make sense? So everybody say thank you. You're welcome. I, for your holiday enjoyment, gave you an official right angle tool with your paper. So I gave you each a right angle. So what you can do right now is take a look at your gold triangle and take your handy dandy new right angle tool, and if you can compare that to each of your angles and determine whether you have the acute right or obtuse gold triangle. Go ahead and take a minute and declare your triangle acute right or obtuse. Marcus, go. Well, paper is my right angle. Every time I give you paper, I give you 4 gifts. You're welcome. I was like, hey, how'd you find this? Okay, so you have the all right, have we all declared whether we have the acute right or obtuse? Serena says, do you get a right triangle or a right angle every time you pass out papers? Yes, because you are also. All right, here we go. We're gonna have some good times with mid segments. Are you ready? Would you please take your gold triangle, and I want you to match a vertex to vertex and pinch. And dear friends, it's going to look like this. You're going to match vertex to vertex and pinch. After you pinch, you're going to take a writing utensil and you are going to mark what we call the pinch point. You're then going to take another side of the triangle, match vertex to vertex, and pinch. Then you're going to take said writing utensil and put a dot on that pinch point. You have one more vertex to vertex, carefully folding along the side and pinching, giving yourself your third pinch point. It's so amazing. What you have now is a series of midpoints to connect, and by connecting your midpoints, you will create mid-segments. Your mid-segment, you will be excited to share and declare, has some pretty cool features. One of the features of your mid-segments, of course, is that it is created from your midpoints of each side. The next thing you care about your mid segments is that it's parallel to the third side of your triangle. And of course, you already know that it's half the length of the third side of your triangle. So those triangle mid-segments become an important conversation in our triangles. So you have a straight edge, and the straight edges and the baskets, of course, are easier to use, but we want to make sure that you draw nice bold lines. We want to make sure that you've pinched equitably. We want to make sure that you understand what a mid segment is, and that should be reviewed, right? Right? Triangle mid segment. You got it? So make sure every group member has a green triangle. Your triangles that are green, everyone, one of you has an acute, one has a right, and one has an obtuse. So declare what you have to your group mates. I have the. So you are going to create your perpendicular bisector. When you create your perpendicular bisector, you are going to again match vertex to vertex. Make sure that your edges line up so nice and neatly. And then instead of just pinching, you're going to fold. So you're going to make a lovely crease, pressing your finger down and tracing. And then you're going to spin the triangle, and you're going to fold over the next vertex to vertex. And you're going to again crease. And then you're going to spin the triangle and match up your third set of vertices, vertex to vertex, and crease. Take a minute to do that. So here's what's super amazing. When you take your straight edge and you draw along each of those creases, you are drawing along the perpendicular bisector of each side of the triangle. Now, here's what I want you to pay attention to. Two lines intersecting is no big deal. In fact, unless they're parallel or skew, it happens all the time. But here is the holy cow, wow part of this conversation, and that is the fact that all three lines intersect. Now, I just went around and handed a second triangle to everybody with an obtuse triangle. Because for my obtuse friends, check out over here, your choices, would you like to recreate it with an acute or a right triangle, where the holy cow wow point of concurrency is visible? Or you can take a separate piece of paper, because those perpendicular bisectors will intersect outside of the triangle.
I'm getting a perpendicular bisector with all three vertices.
You absolutely are. Here's a perpendicular bisector. Here's a perpendicular bisector.
I don't know how to draw.
So my So Sammy's like, mine's not working out. He's got a right triangle. Hey friends, if you have a right triangle, your point of concurrency is on the hypotenuse of the right triangle. If you have an acute triangle, your point of concurrency is inside of the triangle. If you have an obtuse triangle, those perpendicular bisectors will all meet outside the triangle. So let's talk for a minute about what mathematicians discovered in this minute. If we talk for a minute about what they found, it's pretty darn amazing. Because anytime you have two lines, unless they're parallel or skew, of course they intersect. No big deal. Commonplace, happens all the time. But if I have this third line, I want you to think about all of the places that it could possibly intersect one or the other of the lines. It could be here all the way around. And did you notice that your third fold went right through this one point? Hey friends, that's a holy cow wow moment. If you're a geometry scholar and you're looking at the perpendicular bisectors of a triangle and you're like, oh snap, it goes right through the middle. Hey, has that ever happened to you? You're at 7-Eleven and you're ringing up whatever you're buying and they go, that'll be $6 even. And you're like, even? You're so surprised. You have a 1 in 100 chance of it being 0 cents, right? And you're shocked. Even? Seriously? No change? No change. $6 even. You're shocked. I want you to imagine hitting this point out of infinity. Holy cow! Are you kidding me that those perpendicular bisectors all cross through this same point? And imagine these geometry scholars going, did it happen for you? 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 For you? For you? For you? No, wait. How big is your triangle? Did you make a big triangle? Did you make a little triangle? Did you make a right triangle? Did you make an obtuse? Did you make an acute? What kind of triangle did you make? Are you kidding me? This happened? Wait, with every triangle? And imagine they spent days, weeks, months messing around with triangles, drawing perpendicular bisectors. Does it happen every time? What's the answer? Yes. They couldn't believe it. The perpendicular bisectors of all three sides of a triangle will always intersect at a point on the triangle, in the triangle, outside of the triangle. Depending on if it's acute, right, or obtuse, they'll always match up into what we call a point of concurrency. Everybody make sure now that you have a blue triangle. Your blue triangles are going to represent, you're going to fold and create your angle bisectors. Instead of matching vertice to vertice, you're going to match one side to another, and you're going to fold the angle in half. You're going to repeat for each triangle vertex. This should probably say vertex. You're going to use a straight edge to trace along each angle bisector. And you're going to see something pretty amazing. Are you ready? Here's your blue triangle. And what you're going to do is you're going to match up side to side. Do you see how I'm folding? Side to side. If it's easier, especially for these skinny, tricky angles, if you take it and like pinch it, that gets you started on your fold. You're folding each angle in half. Rotate the triangle, and you're holding on to the vertex and folding the triangle so that your sides match up. So if you're having a hard time, think about pinching this angle and folding it in half. Once you have all three creases, you're going to take your straight edge, and I should here some exclamations of what? Come on. What am I hoping to hear? Louder, Nick.
Holy cow.
Holy cow, wow.
Wow.
Because check it out. When I trace my angle bisectors, are you kidding me? So wait, stop. Geometry scholars across the land are freaking out. Holy cow, wow. Who needs help? Do you have the angle bisectors?
Alright, so show me not at all stressful.
You get it? Pulling the angles?
You have to have it.
This one.
Go in.
No.
Yeah.
Mine is slightly off.
Wow! If this isn't long enough, you can move this straight up, right? Holy cow! Why aren't I hearing you? Holy cow, wow.
Oh.
Listen. It's fine, we're saving it. You see it? Check this out. Wow. Cute. Weird. You can totally see where it is.
Holy cow, wow! Hey, it's not every day you get so many holy cow wow moments in one class. You see it? So here's the deal. I want you to imagine something. Who cut this? Back to kindergarten.
You start a internet page, HHS covers.
It's fine. We'll just
Did I
face
tell
the
you about the
one.
parking lot?
Yeah.
I don't think it's good.
Yeah, same with my sister.
They have parking lot shading here?
Yeah.
Yeah. There's posture check.
Posture check is going
My son's on.
Yeah.
You cut the yellows.
Good. That one was terrible. I made it.
Okay, so again, I want you to imagine, mathematicians across the land going, stop. It happens with angle bisectors too. Stop. Are you kidding me? We had a holy cow wow moment with both angle bisectors and perpendicular bisectors. That is crazy. We had an infinite number of places that this third one could have crossed. And are you telling me it crossed at exactly that? And they're like, yeah, that's exactly what happened. And then just like a Ginsu knife commercial, they say, but wait, there's more. So what's next is your medians. And you're going to create your medians on your pink triangle. So again, pass the pink triangles out. Identify, call it out, tell your friends. I have the
Obtuse.
cute rider of twos. Test it with your right angle. Ready? That's definitely a two. See it? That's an obtuse angle. Holy cow. All right. No, we're doing medians. Medians. We're back to pinching, my friends. You're going to match one vertex to another and pinch. You're going to match the pinch point with a dot to represent the midpoint. And you're going to repeat this for each triangle side. Then you're going to use a straight edge to connect each midpoint to the opposite vertex. So you're going to match up vertex to vertex and pinch, vertex to vertex, and pinch, vertex to vertex, and pinch, and then you're going to mark each pinched spot with a dot. And then here's the tricky part. You're going to get your straight edge and you're going to connect vertex opposite to pinch point. Now, you might need to use your handy dandy created straight edge because the ruler might not be long enough. If it is long enough, it's easier to use for sure. Excuse me. If it is long enough, it's easier to use, but you might have an instance. OMG. What? Say it with me, everybody. Holy cow. Wow. Concurrency. Hey, that's what this is called. This is called a point of concurrency. Now, for this triangle, there's a particular challenge. Are you ready? This triangle, that point of concurrency is the perfect center of the triangle. If you put your point of concurrency on your finger, you can balance the triangle perfectly and it won't fall. So go ahead and play with your point of concurrency. Okay, next triangle center, we have our purple triangle. So what we're going to do for this one, let's go ahead and move on and talk about our purple triangle. Find an official right angle tool. Now, for those of you who maybe weren't with us mentally, here's a hint of where we can find an official right angle tool. Your instructions are as follows. Your instructions are as follows. You're going to align the tool along a triangle side and an opposite vertex. Then you're going to use a straight edge to trace along the segment. And you're going to mark where all three lines intersect. So there, I just gave it away. It's going to happen again. Here's what I mean by I have my official right angle tool. There it is. Watch, then do. I'm going to align my official right angle tool along the side of my triangle. Then what I'm going to do is I'm going to slide it, making sure that it's still along the side of my triangle until I hit my vertex. If I do that and I'm lined up down here along this edge and I'm lined up here at my vertex, then this line that I'm about to trace will be what I'm looking for. So I'm tracing my, what is it? Come on.
Wait, can we not use the obtuse one for this?
I'm tracing my altitude. So the interesting thing is, I just heard somebody say, hey, can we not use the obtuse one? Yes, because tracing an obtuse angle bisector or an obtuse altitude means that it happens outside of the triangle. So what you're going to do again for those people that are still talking while I'm instructing, boy, that's frustrating. You're going to line up your edge of your right angle tool along the side of your triangle. Then you're going to slide, and in this case, maybe it's either easier to slide the triangle. I'm going to put the triangle so that this edge goes into the vertex. So I have this edge down here lined up, and then I slide it so it goes through the vertex. And then when I trace along this straight edge, and if it's easier for you to get a straight edge, then you know that that edge and that angle are lined up. Because this is guaranteed to be a right angle because I measured it with my official right angle measuring tool. I've done this one. Now it's time to do this one. I'm going to line my straight edge up with the base of my triangle, and I'm going to slide it over till I hit my vertex. And then I'm going to, if it's easier for you to get your straight edge, go ahead and do that. Because now when I connect my lines, what? Are you paying attention? You have another holy cow wow moment. All right, so I want your white paper out, and we're going to take some notes on this so that we can talk about each of these triangle centers and the amazing cool things that happen as a result. So make sure you have your paper out while we talk. Everybody good? All right. So the first thing that we need to understand is these triangle segments. We're going to have to know 5 of them. And I got to be honest with you, the assessment that comes with this one is one of the harder ones. That comes with, stop that please. The assessment that comes with this part of Unit 5 is particularly tricky. Because it's a lot to remember, it's a lot to process, it's a lot to use. So we want to make sure that you have all of the notes necessary. So we're going to be talking about each of the triangle segments. There are 5 of them. And as we talk about them, I want you taking notes on your triangle and on this white piece of paper. So our mid-segments are different because they don't have a point of concurrency. Our mid-segments create that inside triangle. There's no point of concurrency, no holy cow wow thing happening with our mid-segments. When you talk about our segment and angle bisectors, our medians, and our altitudes, they do give us a point of concurrency. And it really is such a special moment. We named each of them: circumcenter, incenter, centroid, and orthocenter. And those are going to have to be words that you remember. So it's hard because those are new words, but you're still going to be completely responsible for them. All right, let's go down and talk about medians first. Your medians were your gold triangles, so take that triangle out, please. And when you had your gold triangle, you went ahead and you found the midpoint of each triangle. And the midpoint of each side, then, you connected to the other midpoints. And the thing that was pretty cool about this was you learned that each side is parallel to that third side opposite, and then you have all kinds of congruency. This side is the same length as this side plus and this, which means that there's that 1:2 relationship between the lengths of the sides. Once you start matching up all of the congruent sides, you realize, oh snap, check it out. I end up with 4 congruent triangles. I end up with a congruent triangle here, 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 and here. A That's pretty cool. So there's conversations about mid-segments. There's conversations about mid-segments. We have that it's parallel to your third side. And think about that parallel relationships giving you all those angles that come along with it. And then it's half the length of the third side. Which means if somebody gives you one measurement, you can responsibly come up with all the other ones. Everybody got it? Mid-segments, we've already talked about. Those are your gold triangle. And whether you have an acute or a right or obtuse angle, it does, or a triangle, it doesn't matter. As long as you connect the midpoints of each side, you end up with those mid-segments. Everybody got those notes either on the triangle or on this white page? Give me a thumbs up, let me know you're good. All right. Next comes our perpendicular bisectors. Our perpendicular bisectors were our green triangles. And in fact, I went around and passed out extra of these because if you have an obtuse triangle, your perpendicular bisector ends up outside of the triangle. And if you wind up with a right triangle, whether it's obtuse or whether it's right or acute, that perpendicular bisector is not always in the same spot. All right, when we created this one, we still found the midpoint. We still found the midpoint. Come on. We still found the midpoint, but instead of pinching, we actually went ahead and we folded on that midpoint with each side. So we found the midpoint and we folded. We found the midpoint and we folded. And then we ended up with a holy cow wow moment of, wait, are you kidding me? All the places that these lines could have intersected. Now you can see when I'm drawing, they don't always come out exactly perfectly because I'm estimating, but the folding took care of all those estimates. No need to estimate. No need to estimate when I'm folding because those were more precise measures. Okay? Everybody okay with that? When we have our perpendicular bisectors, that point of concurrency where all three lines intersect, we were shocked and amazed that that happened. We're going to call this one the CIRCUMCENTER, the circumcenter. And the circumcenter is actually pretty darn cool. I'll tell you why. Because that center point represents the exact center. Is this going to let me pick this up? Nope. Hold on. Oh, drat. How do I make it? Oh, I know. Hold on. Darn it. Hold on. I'm having a hard time. We'll try again. That circumcenter actually represents the exact middle point of the circle that connects each of the vertices of the triangle. So if I had that purple circle that goes around and touches each of the vertices, the exact center of that, now I can't get it to let go. The exact center of that is here. So that means that the distance to each of these vertices is the same. We're not surprised by this because when we talked about the distance on the perpendicular bisector to the endpoints of the segment, we knew it was the same. So what we know here is that it is equidistant to each vertex. And that is your point of concurrency. That point of concurrency is called the circumcenter. That circumcenter is where those lines intersect. And that, my friends, is going to be equidistant to each vertex. That's pretty cool. Okay, our next, that was our perpendicular bisectors. Next comes up is angle bisectors. Our angle bisectors was your blue triangle. And all of those, again, marked in one place. And that is called the in-center. And our in-center was when we had a triangle. And we went ahead and we divided each angle in half. And when we divided each angle equally in half, by folding, we were shocked and amazed to see that again, each of those lines intersected in a point of concurrency. Now those angle bisectors, they continue on. They have these little tails that go on past the dot. But that's not really what we care about. What we care about the most is the fact that each of these happens to be equidistant to the side of the triangle. And that equidistant measurement is done with a perpendicular line that may or may not be the same as the tail. Because they are equidistant to the sides of the triangle, we can end up, again, using a circle as the center and recognize that you can draw a circle inside. That's why we call that point of concurrency the in-center. That circle that we can draw inside has the center that is the in-center. This in-center is equidistant to each triangle side. That point of concurrency is found where all the angle bisectors intersect. And again, that's a holy cow wow moment. Geometry scholars were shocked. Does this happen for every triangle? Yes. So the interesting thing was whether it's acute, right, or obtuse, it doesn't matter. It's always, this point of concurrency is always inside the triangle. With our circumcenter, our right triangle is on the triangle. Our obtuse triangle is outside. Okay?
What do you mean by each triangle side equidistant?
This point of concurrency is the same distance to each triangle side.
So this one can be
The distance from the point of concurrency to the side measured with a perpendicular line. Alright? Now we get to talk about our medians. And our medians was the cool one. We went ahead and we pinched again, so pull out your pink triangle. And with your pink triangle, we again talked about finding the midpoint, but instead of folding, we just pinched. And instead of connecting these to make mid-segments, I went ahead and I I drew a line from each midpoint to the opposite vertex. And I was shocked and amazed again to find what?
They all meet up.
Yeah, another point of concurrency. I'm like, are you kidding me? I get another point of concurrency. These really intersect again. This one we call the centroid. And we played with it, that point of concurrency is the point of balance of your triangle. So you went ahead and you balanced it on your finger, you balanced it on an eraser, you balanced it on the top of your pen or pencil. That was what was fun about the pink triangle. And that represented each midpoint to the opposite vertex. Now the medians have an extra little conversation, so what I'd like you to do is everybody take your pink triangle out, please. And I'd like you to take a straight edge that has some kind of measuring device. And I would like you to measure the following distances for me. Pick a median, any median, it doesn't matter. And I want you to measure the distance from the median to the side. This is measurement number 1. And then I want you to measure the distance from the median to the angle. That's measurement number 2. So I want you to find distance number 1, and I want you to find distance number 2. And centimeters is probably the easiest for you to use. But I would like you to talk about those distances with your friends. How far are they? Measure those distances. I can be a fortune teller, and if you call out what your number 1 measurement is, I'll guess your number 2. If you call out your number 2 measurement, I'll guess your number 1. Who wants to play?
6 centimeters.
Was that your 1 or 2?
Which one's 2?
The longer.
Then that was the short one.
If 6 centimeters is the short one, his long one was 12.
286.
296 centimeters? 86? So that's 400 plus 160, that's 560 plus 12, that would be 572.
Yeah.
Because what is true about this measurement? Come on. 2 is twice the length of 1. Now, the way that the mathematicians present this, I think is more confusing than the way that I like to understand it. So you tell me your opinion. That centroid divides that point of concurrency, named the centroid, divides the medians into a segment that is 2/3 the distance from the vertex. I find that confusing. What I would rather do is recognize the fact that segment 1 is half of the distance of segment 2. So if I had a measurement where this one was 3, what would 2 be? Yeah, because it divides it into 3 equal parts. So that distance from the centroid to the vertex is 2/3 of the whole. The distance from the centroid to the side is 1/3 of the whole. But you can see that I have this relationship of 1 to 2. That ratio of 1 to 2 for my centroid. Okay, real quick, let's talk about the altitudes. When we found an official right angle tool, and we measured the altitudes of our triangles, it was kind of boring if you happen to have a right triangle. But if I had a acute triangle it was pretty cool because if I drew the altitude of each side, Sumner, stop it. Then we had our fourth holy cow wow moment of the day because each of those altitudes intersected at a point of concurrency. This one is called the orthocenter. So this one is kind of boring. There's not really a whole lot going on. All that we need to know is that each of these altitudes represents the height of the triangle. We don't necessarily have any cool stuff going on, but we do understand that if our triangle was obtuse, that point of concurrency happened outside the triangle. If our triangle was right, that point of concurrency happened right down there at that right angle, because each of those legs is an altitude. So that's kind of cool. A few fun facts for you. If you have an acute triangle, all points of concurrency are inside of the triangle. If you have an obtuse triangle, your altitudes and your perpendicular bisectors, that point of concurrency will be outside. Your medians and your angle bisectors will be inside the triangles. If you have a right triangle, your perpendicular bisectors, your point of concurrency will be on the hypotenuse. And if you have a right triangle, your altitudes will be on the right angle. That's where your point of concurrency is going to be. All right. So we don't necessarily have any homework for you over break because we're going to revisit and take official notes on these next time that you're going to use. So what I saw a lot of kids doing was tucking their 3 triangles into the pocket of where their straight edge was to help kind of keep it. If you want to put it in a folder. Some people went over and hole punched them to keep them in a 3-ring binder. Make sure you have your 3 triangles, no, 5 triangles to talk about. Please don't talk so I can finish. What I'm passing out to you now is a review packet for units 1 through 5. It is your choice. I can't yell over you guys. By the end of the day, my throat is killing me. Now, this is not due next class. But if you are one of those people who wants to review or look at stuff over break, I want to give it to you now. I can't talk over your packing up. So just sit still. We have 10 more minutes of class. It's not time to pack up. It's not time to leave. Would you be upset if I took your paper away from you 9 minutes early? If you were taking a test? Most likely. I get my 9 minutes. So the packet is a culminating packet of 1 through 5, units 1 through 5. It does not include these triangle centers. It is going to be due and collected, not next class, here we are today, not next class, but your packet is due on this 6th. So it's your choice if you want to work on it after break and take a break, that's fine. If you want to work on it a little bit over break, that's fine too. There's been lots of questions about a midterm in geometry, so I want to make sure that you have all the information you need while you're holding a review packet. Yes, there's a midterm in geometry, and yes, that's a good thing. Geometry, especially at the honors level, has too much to include on one test. So what we do is we give you half of the midterm halfway through the year. We give you half of the final halfway through the year and call it a midterm. So chapters 1, 2, 3, 4, 5, and 6. We still have another unit to go before the midterm. We will do that in January when we come back. Your midterm will include unit 6. This packet takes you all the way back to unit 1. I would like your goal to be to get yourself organized. Spend some time going back through your notes. Everything is posted on Schoology. Everything is available here. I've had a couple people stay after school with me and take advantage of that. Okay. So if you are not organized, would you please make it your effort, your goal? Call it a resolution to get organized so you have all of the things that you need. Alright. Would you please return? It's so frustrating. I know it's the end of the day. I'm tired too. If you have extra triangles that you don't need, I'll be glad to take them. Please don't crumble them up and leave them in the baskets. Please do not put trash in the baskets. That just means I have to pick it out. If you have my scissors still, please don't put that in the basket. I want them back here. You know what happens if I leave scissors in the basket? No, they cut my baskets. No trash in my basket, no scissors in my baskets. Please. Go ahead and pack up and take 5 minutes to chill. Go.